Hi everyone. So what I'd like to do in this video is just go through the memo for this question because this is something that is very, very important, not just for this module, but even for second year. So the correct answer that I was looking for is this one given here at the bottom. Okay? So a lot of issues arose mainly when it came to this part here, right? So that's what I want to clear up because a lot of you lost marks there and I want to show you where. Okay, so remember we need to always start off with the definition. The definition of the PDF is f of y, which is just a function of y, which will give you the probability that y is less than or equal to some given value of y. So more generally speaking, that is the area under the graph from minus infinity to y. It's the same lowercase y every time. In order to find that, you need to integrate your PDF. In this case, we replace the y with a t, and I'll explain that just now. And the reason why we do that is because y is already here representing a specific value. So you cannot use y in here because y, if you put it in there, it's also now going to represent your variable. So you need to put a placeholder. So you can put t or x, whatever letter, it doesn't matter. So now the idea is to always get the area to the left of the value of y. But notice it's going to depend on which region of your number line it is. So think of it like this. You have a whole number line and y can take on any value between minus infinity and infinity. But notice here for different regions, you have different functions. So you need to make sure you account for that. So for 0 to 1, you have a function there, which is this one here. And then from 1 to 2, you have a different function. So I'm just going to use a number. So this is function 1, which is actually the 0. Function 2, which is going to be that 0.5y. And then you'll have a third function in there, which is 0.2y cubed. And then a fourth function, which is your 0 again. So let me write it there. So this is 1 and 4. So now if you want to get the area to the left of y, it depends which region it is. If it's in the region 1, y there, then you need to integrate from minus infinity over there up until the value of y, right? But then the graph in region 1 is 0. So that's how you always get 0. Okay. I think it depends. Actually, rather, let me not say it always is 0. It depends. Whatever function 1 is, you need to read the question. Okay, in this case, it's 0. Then you need to consider region 2 here. So let's say y is over here. Then remember, you want all the area to the left. Okay, so you must integrate over region 1 and from 0 to y. Okay. So you end up with a 1 and a 2 for that one. So here, you know that in region 1, though, the function is 0. So there's no probability there. So we're not going to waste our time there. Let's focus on this function where we integrate over function number 2 from 0 to y, the given value of y. So here, it's from 0 to y, okay, over 0.5 t dt. So not 0.5 y, 0.5 t dt. And then when you complete the integral, this is what you get. And I think most of you had that correct. Cool. So now if y is in this region 3 now. So let's say someone says I give you 1.2. If you wanted to find that probability, then remember we still want the area to the left. So this time you're going to integrate over function number 1, 2, and 3, but only up to y. So you'll have minus infinity to 0. You must have 0 to 1, and then you must have 1 to y. This one we know is already 0 from the question, so we just need to make sure we get that one and that one. Okay. So that's how now if you look at my formula here and my calculations, so we need to integrate. So the first integral where I have over this one here, this is the one I'm talking about, okay? This is that one, and then this one is that one. So this is where most of you lost marks. You always, I don't know, as students, the tendency is always to leave that one out. So I'm being so emphatic here for you to remember. You need to remember to include the area in all the previous regions as well. So don't just integrate from 1 to y. You're going to leave out any area to the left of that if you only do that. So remember, this is so important. Okay, so remember we need the area. So notice here from 0 to 1. So the integrals from 0 to 1. And then here we have your t dt, just following from our definition. Cool. And then for the other one here, it's between 1 and y. So you'll have 1 and y, but it's over function number 3. So remember, this is function 2. This is function 3. All right. So when we were marking, you were penalized if you forgot to change this. Then you lost a mark there, or a partial mark there. Or if you had the wrong bounds, you also lost that. Similarly here, if you had any error, like you forgot to put the wrong bounds, or if it was missing altogether, then you lost marks there. So watch out for this. All right. Most of the marks in the question were for this part. Yeah, most of the work actually is there. So let's go back now. For once you've done the integral, we'll just finish off. This is what you get, right? And then the last region is, what if someone gives you a y that's in here? Then remember, we always want the area to the left. So that means you need to integrate over function 1 from minus infinity to 0, function 2 from 0 to 1, function 3 from 1 to 2, and then function 4 from 2 to y. But we're not going to waste time with that one. We know it's 0. How? And also, if you look at this graph, we know all of the probability lies between 0 and 2. Because if you look here, it's 0 below 0 and above 2. So there's no area under this graph anywhere outside of that region. So you're not going to waste time actually doing any of these integrals. But if you did, you would integrate like that, all 3 of them, and you'll find that the answer is 1. So I don't want you to waste time on the last one. If you reach the end and all the probability, you're sure it's to the left, then you can just go and write it. So that gives you now your final answer. When you put it all together, this is what it looks like. So that's really what I wanted to emphasize. Whenever you derive a CDF, this is the general process here. You make sure you divide your number line like I did here. Divide your number line according to these intervals that you're given. And then you consider y in every single region. Okay? And then from here, you need to now take all the integrals to the left. So if you're looking at y in region 2, okay, so let's say you're looking at this y, then you must integrate over region 1 and 2. If you're looking at a y in this region, then you must cover 1, 2, and 3. If y is in the next region, you cover 1, 2, 3, and 4. So you always cover every single function to the left of y must be included. The last one must always be from whatever that lowest bound is before the y up until y. So you'll see that pattern. All of them always end with a y, okay? And then all the ones in between are the ones which will now have the numbers at the top and the bottom. So that is generally the idea behind it. So you can just learn that method as well if it's going to help you. This will help you just remember. Okay, so that is basically what we were looking for. I wish you all the best.